Hi, and welcome back to the book club. And in this one, we're actually still in this interstellar travel book where, well, the book is written about how to go to other solar systems. A lot of what's talking about will be very important in sort of the space economy, especially if we want humans up there. Now, I know I talked about how, survey says 80% of people think it will really be robots who do a lot of this. I'm that sci-fi nerd. I dream about the part that we're going to have humans involved. And certainly, I do believe fully that there'll be human colonies and things on Mars. But this one specifically want to dive into the environmental control and life support systems of it, because this is really, if you think through the ability, say if we're going to go colonize the moon, colonize the Mars, a lot of times we just think from it from a propulsion point of view or things like that. But there's actually, as we kind of highlighted the last time, the medical science side of things is pretty hard to do, and specifically here now, and just sort of taking, keeping the humans alive, will be really interesting. And the first one is actually, it's called because the rule of threes or law of threes, okay? And primarily, it goes like this: 3 seconds. That's how long a human will survive the vacuum of space. So the complete vacuum will just, right, you'll kill you, you'll boil your blood and all that different stuff. So 3 seconds in the harshness of space. 3 minutes is about what it takes if you don't have oxygen. So you might have pressure, but if you lose your oxygen system, too much CO2, your spacecraft, you're gonna stop breathing. Okay, 3 days is usually what it takes if you run out of water. Okay, that's humans can dive in without the water. All sorts of things start shutting down, but along the process. But that's usually where you sort of have it. And then the last one is 3 months, and a little bit of breakdown here, but 3 months is food. However, sort of within that, really, it's something like within 3 hours is really where you start switching over to your fat, and then 3 weeks, like sort of switching kind of from sugars to fat. 3 weeks is where you really start having a tremendous shutdown. You're really starting to just tear yourself apart. So you might last 3 months, but it's pretty brutal. In fact, if you ever watch some of the good survival shows out there, you really get an appreciation for some of this. Especially as they, like, step one for them usually is like finding a source of water. Shelter comes along here too, if you're in a survival show from the elements and from predators and things like that. But this is a pretty important part. And so, also, as we look into it, really, this is from NASA. This is the list of all of the things that we need. And so I'm going to write them here so that we have sort of the ongoing list. But, of course, there's air, water, food, thermal. We will talk about, oh gosh, it's off the screen. Air, water, thermal, waste management, and then crew accommodations. Okay, we're going to kind of talk through all of that, but this is sort of the list. You can look here in terms of kilograms per crew mass in days, in terms of what's needed, in terms of the overall air, in terms of the carbon dioxide that you produce, the air that you're consumed, both here on the food side, the food that you're consumed, the energy content, the potable water that you need to drink. On the thermal side, there's metabolic heat, sensible heat, waste, right? Your fecal matter, your perspiration. On the solid side, also your some solid waste does come out through the urine, and then of course within the water system, there's the fecal matter, and then respiration, perspiration of water, and urine. So this is sort of the full map of what it takes really to take a human alive. And again, I want to celebrate that we've had a space station up and running for about 20 years. So we've really honed in and learned a lot about this along the way. And this is just a kind of a broader example of all of this when we talk through all of the process. So you have the humans, from the waste management to the urine processing and recovering of the water. You see the air, the oxygen and nitrogen. We'll get into some of this, the control of it for oxygen generation, so that the space station actually uses electrolysis and the Sabatier process. I'm probably pronouncing it wrong. And so there's methane as an exhaust. You have to purify the air. So I'm going to get into a little bit more details on some of this. So I'll kind of leave this diagram here in the corner. But for a lot of this, we'll actually start off here with the air. Okay. You're going to have to store a bunch of air. There's just no way around it. And usually the way to do this is in some sort of cryogenic form, just that way it's condensed. But you're going to want to have it sort of separated for failure modes and things like that. A quick diagram over here is going to show you like you need some sort of buffer gas. So yes, well we've had some mercury gas, so we did run 100% oxygen. The fire can be pretty, 100% oxygen environment is pretty rough in terms of fire risk. And then we've learned a lot in terms of sort of what pressures, so 14.7 is sort of sea level, PSI, what pressures are we able to kind of go at. And a lot of times, and I forget the number now, where the space station actually holds itself to. That way they can kind of go in and out of your when they're doing spacewalks faster. And so some of it is, a lot of that preparation for a spacewalk is sort of dropping the vacuum so you don't get the bends quickly. So you have to kind of suit up and stay in that low pressure environment. And so that's a pretty important one. So you need the cryo, you need the buffer gas. Okay, and for us, it is nitrogen. I've done some scuba diving. There are some depths and things like that where you can actually go to a tri-gas. So it doesn't always have to be nitrogen, but there's some balances there. Okay, and then really, as I mentioned, there's the sort of the fire risk that you have to combat against this. And if you do have a fire, right, that's going to eat up a lot of oxygen. And so back to the reserves point of view. Okay, and then the pressure is important. So cryo, buffer, fire, present, and then pressure. Okay, so those are kind of the big ones from the air point of view. Now, water is probably one of the hardest ones here. So right now, our current water recycling process is about 98%. Now, it said the human handles about 4 kilograms. So say if your normal human is maybe 70 to 80 kilograms, use 4 kilograms a day. So what happens if you go do the math, if you think through, say, this 2.5-year voyage to Mars, where you go to Mars, you stay there for a while, then you come back when the Earth and Mars are more aligned. It's something like if you're going for 2.5 years, you end up at this 98% recycle, you end up having just a ton of water that you have to carry for just the humans, because 90% is not that high. And in the Interstellar book, they were talking about like even longer missions than that. It gets pretty brutal. So there's a lot that has to go here. That's from a pure recycling point of view. But there's all sorts of systems, right? I've served on some Navy ships as a maintenance in my reserve capacity, and so I'm familiar with all of the things that the Navy does just to be able to provide clean water and then the holding systems and things like that. But it's also with an open environment. You have sort of salt water around you and power that you can use. Okay, so there's a diagram here. So this is sort of just your generic sort of civil water treatment plant, but you have to go through all the processes of sterilization and filtration and separation of all the aeratics, and then final chlorination to kill things, and usually there's also the UV light to get down to a lot of the microbes before you would ever kind of push it back into the supply. So all of the stuff that you see on land that is big, huge things has to happen in space, which then is aerospace grade and takes a lot of mass. And so this is a big one, okay? And again, all of the sterilization, filtration, all of those things. And some of this stuff, like this 98%, it gets pretty hard because, again, there's some solid waste that we actually have in our urine, and so it can get really hard to kind of crack some of the last little bit. So there's some neat things that are coming out, some neat advantages. What we do right now in the space station is sort of basically chemical-based. There's actually some pretty cool ones that are coming out that are more biological-based. And so there's some exciting research happening, and the European Union is doing some stuff, as well as NASA. Using more like biological systems, like kind of mini versions of what we would have here on Earth. They're pretty exciting. Okay, from a food point of view, let me get to the blank screen again. Back to here. So from a food point of view, of course you have to carry this, for sure. You can think through if you go to sort of these more biological inspired processes for the thermal. Maybe you're growing algae. Maybe there's some sort of closed cycle, depending on the size of your spaceship. Maybe you're getting to the point where you actually are able to grow some food, and they are doing a little bit of that in space. So maybe that's part of your cycle. You can incorporate it. You could do some CO2 scrubbing. But food is a big deal to just carry. But most of this is the interesting point, most of the down mass, I'll just say waste here. Most of the down mass, this is stuff that we're sending from the space station back to the Earth, is actually waste from the food. It's the wrappers, it's all of the things that we sort of use to sort of keep the food packaged, prepared, clean up after you're doing the dishes and things like that. Almost all of the down mass we're sending away from the space station is waste products from the food and the food processing. So that's a big deal. So if you have this long trip to Mars, maybe just tossing out the airlock. I don't know. That's certainly a mass efficient way to do it. Okay, but there's quite a bit of mass that goes on there. From a thermal point of view, we humans aren't that tough if you really want to think about it from that point of view. There's this sort of this range here between temperatures, dry bulb temperature. This is in Fahrenheit. Sort of, it says like 60 to sort of 80 is roughly where we like it, and then certain range of humidities. That's really our comfort zone. You get outside of that, we don't like it too much. And yes, some clothing can help, but if you ever done some stargazing, you go outside and you're like, you wait like 45 minutes kind of stuff for your eyes to start to adjust, and you're sitting still and looking at the telescope. You quickly realize, like, and I've done this a few times, you go outside and it's 55 degrees and nice clear night, and you quickly realize you should go get your winter jacket, because just sitting in 55 degrees, not actually doing anything for an extended period of time, without a campfire, you're not doing all that stuff because you're letting your eyes adjust. It gets cold pretty quick. So the thermal management point of view is a pretty tight range for humans. Okay, and then from a waste, this is actually the human waste. I know we talked about food waste here. This is things like urine, which there are some solids in urine, and then fecal matter, of course, and kind of what do you do with it? If you've watched The Martian, sure, maybe you collect it and you can use it as fertilizer. But that's an entire process that again, I've seen it on the Navy ships, what you have to do in terms of kind of catching and holding, because the Navy is not allowed to, the kind of international rules, you're not allowed to sort of dump when you're so close to ports. So if your ship is in port, you're supposed to sort of catch and hold. So it's called CHT tanks, catch and holding tanks, where you're supposed to hold all that stuff until you get out to sea, and then you can eject it. Okay, so this really adds up. And then the last one I'll sort of say here is on the crew systems. This is everything you can think through. It's lighting. Okay, we humans need a certain amount of light. It can affect the moods as well. Our circadian rhythm based on sleep cycles and things like that is important. The book gets into it. Clothes. Okay, there are some clothes that give off lots of lint, which then will plug up your air systems. There was actually, no kidding, some like sort of space grade clothing is important to not overload your air scrubbers. Okay. And then what do you do with the clothes? If you're doing all of that laundry, is that now hitting your water systems? And what are you doing with all of the soaps? So this is, you might feel like this is sort of easy. Like, no, it's not. There's actually challenges associated with the clothing, what the book gets into. Hygiene. Are you going to have showers? Maybe that takes up a lot of space. Are you just going to do sort of the wipes thing? Okay. Different cultures, by the way, have different hygiene standards. So depending how international the mission is, maybe there's some differences in terms of what people are used to. Okay. Medical. This is depending on the length of your mission and how far away from the Earth you are. Are you just taking a first aid kit, or are you having to take the full surgical medical suite, like a full ER, to handle any sort of emergencies that are going to happen? I can tell you in submarines in the Navy, they certainly have ability to handle many situations, because they're on a mission, and they're not gonna come up to the surface because some sailor got a bad tooth. Okay, they actually have a process to sort of handle those things on mission. Okay, and so there's a lot of stuff that you have to kind of think through. And that's why it's actually, again, in the Navy service, especially for the submarine, before you go back out to the submarine, they absolutely are doing your final you have to do a dental visit, eye visit. Like you really have to. They really try to check all this medical readiness before you sort of get back out to sea, because it can really hurt your mission capability. Okay. Mention laundry, exercise. this kind of goes back to how are you handling gravity. So if you're in zero G, boy, the exercise thing is almost critical. If you have some sort of rotating G, which is what I would imagine will be going to Mars, something like that, that'll help. But certainly you have to have the ability to do exercise, whether it's treadmills or weights. There's, again, long-standing proof for human health that exercise is a very important thing. So you'd have to have room and systems and mass available for that. Okay, so the whole, a lot of what's set here, a lot of these challenges, whether it's air, water, food, thermal, all the stuff, the kind of the big word is closure, right? How do you get this to where it is a full closed system that you send it away and it doesn't have to have resupply? Again, back to the International Space Station is, just right there, and we're able to resupply it. And if something really goes wrong, the humans get into an escape pod and come down. So the challenge of closure for all of these things really adds that mass. And so it becomes quite challenging, and certainly is a field full of opportunity. So again, kind of back to the space economy, one of the reasons I'm highlighting this is while the economies for asteroid mining or solar power, whatever it is that are going to be important, you need to think of some of this is sort of the equivalent of the picks and shovels. The gold rush in California, right? It wasn't necessarily all of the gold people that made the money. A lot of it was the pick and shovels. It was the tools and things that they needed that were in support of the industry, whereas a lot of the money is made. And so I sort of, I'm excited to kind of do this this chapter of the book to really kind of talk about some of the solutions here, no matter what that industry is, no matter where it is, as long as you believe, kind of like I do, that humans will be involved somehow in space. This is some open challenges, which means some potential ways to make money in this space economy, sort of solving some of these open challenges. And so I'll just sort of finish with, there are a couple of sci-fi books that have talked about this, but just genetic modification. Again, we've learned a lot about the human genome, a lot of stem cell research has gone on. So is it possible to modify the humans to survive? There's this great book series, Red Rising, where they actually really get into this, and this whole branch classes of humans. But really, this is a kind of a picture I found on the internet talking about some of the genetic stuff that you could do, where we're just looking at what we already sort of have. So the Tibetans, for example, live very, very high, and we're seeing a gene flip there in Tibetans. They operate with less oxygen. Okay, being able to adapt with less sleep. There's some people, honestly, that need like 4 hours sleep, and so we're learning like which of those humans, why is it not on them? Some people are very insensitive to pain, right? That's a useful thing. Some people just can get completely debilitated. And so, maybe that helps, as this bullet point is saying, maybe that helps limit how much anesthesia you would need for minor operations, that if they could handle that level of pain. Okay, body odor, back to the hygiene. If you can eliminate some body odor, maybe that eliminates the strain on, say, your water system that's needed for hygiene, like showers and things like that. Bones, we've especially talked about gravity and situations like that, but stronger bones for these longer flights, especially if it's going to be in a zero gravity situation, would be very important. Shorter astronauts, I'm 6'4". If you look at the NASA limit, I think I'm maybe either officially 1 inch too tall. It's actually more about I think your torso height for sitting in that. I think it was still sized based on a Soyuz capsule at the time, but honestly, shorter astronauts confined spaces. If you go back and you actually see how tall, how big were the ships in sort of 1942, Columbus sailing the ocean blue, they were pretty small. All these sailors were pretty tiny. Okay? And then just genes for guarding against cancer. We're seeing some of evidence here. It's in elephants. So there's a whole branch here in terms of genetic modification. Yes, you can go crazy like some of the sci-fi stories, or you can just sort of think through some of these fairly, I'll say easy, and no one, maybe not personal opinions. None of these to me look like too crazy of a thing to do, sort of as maybe version 1 before we start modifying humans for different applications. So really, again, this is the whole life support system. I actually see as a great opportunity for sort of that pick and shovel economy. How do you solve some of these open questions? How well you do it? What's the reliability about it? This is going to be a very big part of the economy, especially as humans head out in outer space. So we'll see you again next time on, I think I've got one more version for this book club, this kind of short little one on the space economy, and we'll see you then.